Hello everyone, I'm Riccardo Ferrari and I'm Team Polyverse team leader, also in charge of the aerodynamic design, control surface design, technological analysis and in theoretical infrastructure network. We are here today to present our project named KAIROS, born thanks to the Royal Aeronautical Society request for proposal, and I would like to take just a short amount of time to present my fellow colleagues. Without them this project wouldn't be possible, and so we are Team Polyverse and these are my fellow teammates.
Hi everyone, my name is Karim and I'm the software and systems engineer.
Hello everybody, my name is Lorenzo and I am the structural and propulsive engineer, also engaged with safety and maintainability analysis.
Hello everyone, I'm Riccardo and I am the aerodynamic engineering, also responsible for the technological analysis.
Hello everyone, I'm Thomas and I'm the systems and management engineer.
Hello everyone, my name is Bruno, I'm a structural engineer.
Project KAIROS aims to face the humanitarian challenge of supplying essential goods and medical support in remote and poor equatorial countries, relying on a full environmental friendly design. Our product is able to maintain a 90 knots speed with an 85 kg payload and 110 km of theoretical range. In addition, KAIROS is able to take off from short soil airstrip with a 260 meter ground run in maximum continuous power. The rate of climb turned out to be at 4.6 meters per second at 1000 feet. And finally, the wingspan is 11 meters with a total fuselage length of 7 meters.
According to competition requirements, the airplane must be full electric, with batteries as the only mean of power storage and supply. Starting from batteries, the team made a comparison between structural and traditional ones, decided to go on with the second type as structural batteries require an expensive composite matrix and are still at an early stage of research. Between different types of traditional batteries, the team selected the NMC lithium-ion batteries, as they have high level of safety, high number of full cycles and pretty high levels of energy and power density. In addition, the team opted for rechargeable batteries, as the swappable ones would create problems during the exchange phase. The total battery weight amounts to 139 kilos, and it has been divided into two different battery packs. The first one of 65 kilos in the front part of the fuselage, and the second one of 74 kilos in the rear part of the fuselage. This splitting is very important in order to guarantee redundancy conditions and balancing properties. Talking about other components of the propulsive system, the electric engine is buried in the fuselage nose and coupled with a single propeller with two blades. The team selected this configuration as it is simple, efficient and easy to access and maintain.
Talking about the wing, the team has decided to use a simple wing, exploiting all the span available with a semi-tapered solution applied at 60% of the span. Naturally, all the decisions rely upon numerous aerodynamic simulation. The team took into account several airfoils, in particular NACA 4412 and NACA 4415, selecting the second one. In addition, the wing has an high aspect ratio, around 10, in order to improve the efficiency and a slightly negative geometric twist angle. What is less common in this design is the use of a flaperon instead of a normal flap. The main reason connected to this design decision is simplicity, with only one row to connect each wing. Moreover, it permits to combine a flap with a very responsive aileron. The only drawback is related to the ability to counter a night crossing situation, but the team, through a forecast analysis of wind in the equatorial zones, did not find a particular level of criticality. This last chapter related to the aerodynamics is the horizontal and vertical tail. In this part, we focus to select the best airfoil using an HAP method upon several parameters. Hence, we have selected a NACA 63012A for the horizontal tail and a NACA 0012 for the vertical tail.
Concerning the structure and configuration setting, choosing a tadpole configuration for the semi-monocoque structure leads to a significant drag reduction. The drag reduction is a paramount, and a tandem configuration adopted also contributes to it while allowing a higher level of visibility and comfort for the pilot, which can safely perform a VFR flight. The space behind the pilot is used either for the cargo or the passenger. In the cargo mode, the seat is reclined, allowing the area to carry the goods, which will be contained in 2 boxes, and system ropes and hooks will safely fix them. In passenger mode, instead, the seat won't be reclined and will be set in the same position as before, allowing space for the passenger. About landing gear, KAIROS mounts a classic fixed leaf spring tricycle, which is practical, economical, and easily maintainable, and facilitates loading and unloading operations, since the aircraft will remain quasi-horizontal when on the ground.
KAIROS must be quickly, easily, and cheaply maintainable. Several design choices keep these pillars above all. In this view, choosing a high-wing aircraft is crucial, as it avoids each operation to be uncomfortable. Batteries are stored in easy access locations, as well as the electric motor and propeller. Loading and unloading procedures are facilitated by the flat floor, thanks to the tricycle landing gear configuration. A full aluminum structure is preferred to a composite one, because of less maintainability and supply chain issues. No anti-burst strike system has been implemented due to its relevant costs and complexity in maintainability. Production costs are estimated on a prediction of a reasonable 400 units produced in the first 5 years. The final selling price ranks slightly below 60,000 euros. Operating costs are then calculated on a yearly basis of 780 flight hours, as the most impacting component refers to the pilot. Given that, the final operating cost is of about 73,000 euros. A further study should be conducted on costs deriving from the infrastructure support network, which are unluckily way more difficult to be estimated.
As a result of the dynamic stability analysis of the aircraft, the handling qualities have been highlighted, and all of them were of level 1, except for the slightly unstable spiral situation, which is perfectly acceptable for certification purposes, and the phugoid, which is borderline between level 2 and level 1, condition which will be perfected during following iterations of the design process. The team also attempted the implementation of a simple LQR autopilot to show the untapped potential of the aircraft dynamic that could be reached with advanced control system schemes and would allow a lower workload on the pilots and better performance, which translates directly into an optimal and smoother execution of the missions.
Regarding innovative air mobility, the team was aware, since the beginning, that it is not possible to think about the aircraft and the ground infrastructures as separate entities. Hence, the team decided to try to think about an optimized solution for a solar farm infrastructure. This was thought as a future development, exploiting a tool for the sizing of infrastructure called RAeS. Trying to optimize the position of solar farms, integrating the function of the aircraft with the function of the local infrastructure and local electric grid. Finally, several future developments are related to possible different uses of the aircraft, for example as a trainer or a transport vehicle, alongside with various geometry modification.